Now, what is it that we want to do? What we want to do is we want to take a word which has letters. Okay, so this word has letters from 1 to some number m, right? So it could be, you should, and the way it's normally done is you take whatever text you want to encode and usually hack it into small segments. For instance, 5-letter words. These would not be words per se, but it would be just from the entire expression that you want to encode, you just take, letter by letter, it's in 5-letter chunks. Okay, so then what you do is you just convert these letters into the numbers. So that's really just the same thing as what we did before. You have the letters numbered, and you just do that mapping. And then what you do is you apply an encoding function. And this encoding function that we do is we take the number that we assign to the letter, we take it to the power e of some particular number e, which we have to determine yet, and then we compute this modulo some number n, which we also have to determine what it is. And so then what we want to do is we want to prove that this is actually a decoding, and then what we want to do as the next step is encode it. So it's an encoding, and then we want to show that we can decode it. So let me quickly describe where these numbers in this encoding function, we have an e and an n. You don't know what that is. Well, here's how we get the e and the n. So the n, we pick a number which is the product of 2 prime numbers. You'll see in a second why. So you pick 2 prime numbers, you multiply them with one another so that you get a number which has, is a number n. Okay. Now, and the example that I'm going to do is 2-digit prime numbers. But in reality, what one does is you pick prime numbers that are 75 digits long. And as we know from number theory, there's an infinite number of prime numbers. Right? And we keep finding new ones. Right? But we take some that are pretty large, actually. So from that number, then we compute what our phi of n is. Now, this phi of n is quite simply put, is easy to find, right? Because it is just the 2 prime numbers, -1 for each of them, and multiply it with one another. Okay, so now this of course is a very large number by itself, but it is one that we can easily compute. However, and I'll come to that later, the prime factorization of any number is a problem which is NP hard. Okay, and that's something that I've just explained in an earlier set of slides, what NP hard means. It means that you need exponential time to compute it. That is not a problem when you have a very small number. Of course, you can compute the prime factorization, but if you get to a number which is 150 digits, that is a very, very tough problem in terms of computational power that you need. All right, so now we determined our n, where we actually picked our 2 prime numbers. That gave us our n. From that, we knew the phi function, and what we now look at is we pick a number e, which is prime relative to that phi function. Okay. Usually you can start with a very small number. You can take, for instance, number 3, 2, or whatever. That doesn't really matter. So a small number would work there. And then once we have that, we have to find these numbers x and y, such that when you have x multiplied with the number e plus y multiplied with the phi function of n, that gives you the number 1. And then I showed you in the last expression that that's something which is straightforward to do. Okay, you just use long division. All right. So now, of course, you say, well, but this is all very hard, but for computers, this is all really very simple stuff to do. So now what are we going to send when we send a message? Apart from the message that we want to send, the message that we send is essentially just the letters, right? The letters are not the letters as such, but they are, because we're sending an encrypted message, it is the encoded version of the letter. So if you have a letter W, if you letter L, you convert it to a number, and that number then gets transformed into some number W tilde, and that number is what we pass on. So we pass on those numbers, and then we pass on the numbers n, which is the number that we picked, is the product of the 2 primes, but we don't tell anybody what the 2 primes were. That's important. And then we send also the number e, which is some number that we picked, right? It's prime relative to our phi function. Okay. Now, how do we decrypt it? Well, what we're going to do is we're going to calculate the function where we take w tilde. So for each letter, we take it to the power of this number e that we obtained, modulo the number n. Okay. Now, again, To be clear, finding these numbers x and y is straightforward for us to do, but inverting this, because you don't pass that information on, is very hard, right? So you will not tell the other side what your x is, and you don't tell the other side what your y is. And you will also not tell them what the p and q is, so that they can't compute the phi function, right? And so the prime factorization, if anybody wants to crack this, is a problem which requires them to impose exponential time. So other than randomly guessing, they will not be able to encrypt it. Or, you know, if you have a quantum computer which can do computation that are in exponential time in polynomial time, then that will be another problem, of course. But we're not there yet. Okay, so now how does this apply? Let me give this by example. So take two prime numbers that we pick, 53 and 59. You can check easily that these are prime numbers. Then you take the product of the two. This gives you my n. So in this case, it's 53 times 59. This is 3027. Now the phi function for this, of course, is just the product of 53 minus 1 and 59 minus 1, which you can put in your calculator is 3016. Okay. Now what we're going to do is we'll select a small number. We'll take one number e that is prime to this phi function. Let's go with a small number. Let's take 3, for instance, right? Because you can see that 3 is not a divisor of 316, so you know that's easy to do. And 3, of course, itself is a prime number. That helps too. Okay, and now we will have to find the numbers x and y such that the computation, so that we can have x multiplied with the number e that we picked, the 3, plus y multiplied with a phi function of n, which was 3016, is 1. Now, you know, I'm not going to go through the math, but you can see that the numbers are 2011 and a -2 would work. No? So, and if you add these two up, this gives you my 1 function. Okay, so now what I talked about earlier, we have the private and the public key. The private key in this case is the number x. This is the 2011 and the original n, so 3027. And the public key is the number e, which is 3, and the number n, which is 3027. Now let me show you how this works. First of all, let's do a satisfactory argument so that we can see that when you receive the number w tilde, you can derive from it with the information of x, because you have the private key. If you know x and if you know all the other components, that you can compute what the true value w is. So what I said in the inversion, what you do if you decode the message is you take w to the power x, or w tilde to the power x modulo n. So let's forget about the modulo n for a moment. Okay, so w, as we encoded, was w to the power e. All right. So w to the power e to the power x is just w to the power e times x. Now we know e times x from the other transformation is 1 minus the function y multiplied with phi of n, the phi function of n. Now we can then simplify this again by taking out the y part, and then we have w times an expression in parentheses. And here's what we apply something called Euler's theorem, which is basically this is akin to just using the number 1. So we have w mod n, and since we assume that w, the word number that we use, is very small relative to the n number, this is akin to the number w. So in other words, this proves that from the number w, knowing x and knowing n, we can derive what the underlying w was.